Hi all, this is my video number 30. I'll talk on the convergence of the Laplace transform. Convergence. Yeah. So we say a function ft has a Laplace transform. Yeah. We say a function ft has a Laplace transform. Laplace transforms. So it means that there is a value, say s naught. With that value, so we have the integral let me write in full better, which the integral, so integral from 0 to the limit, say, goes to infinity, limit L goes to infinity with L there, yeah, e minus st converge as the upper limit, because the upper limit goes to infinity. Yeah, so we say f should be ft here, dt. Yeah, so we say f has a Laplace transform if there is a value s and s naught here, for which that value, when the upper limit goes to infinity, so that integral converge. So in this case, we say that f has the Laplace transform. So now, if we consider the damping factor, if we consider the damping factor, E minus sigma t, right? When sigma greater than sigma naught, say, all right, then those integral limit L goes to infinity, integrate L, E minus sigma t ft dt converge faster than those faster than sigma equal to sigma naught. Yeah, and then if the integral converge at s naught, yeah, and if the integral means those integral that what we have explained, I have explained earlier. If the integral is convergence at s naught, so which means it's also convergence for all s. Yeah. So which means it is convergence. It is convergence for all s in the half plane. Yeah, in the half plane. That real of s is greater than real s naught. So in this case, this implies that there is some value sigma c, there is some value, say, sigma c. So we call this sigma c as the abscissa of convergence. Yeah, abscissa of convergence, such that the integral converge, such that can you see this? Yeah, such that the integral is convergent in the half plane in the half plane sigma greater than sigma c, and for sigma less than sigma c, the integral diverge. The integral diverge. All right, so what we can say, the sigma c is that it's like the boundary where it's separate between the convergence and divergence of the integral. All right, so those sigma or those number, we call it as a abscissa of convergence. Okay, so we have this form here, abscissa of convergence, sigma c, where sigma c separate or make the integral converge for half plane, and for the other plane, for the other half plane where sigma less than sigma c is diverge. So those sigma c, we call it as a abscissa of convergence. All right, then we have the integral, the Laplace integral. Yeah, Laplace integral. We have Laplace integral of f. Let's say fs. This is, we integrate 0 to infinity e minus st ft dt. Okay, and this fs, I mean the Laplace transform of f is analytic function of s. Yeah, is so fs. We have fs is the analytic function of s with no singularity in the half plane of convergence. Yeah, with no singularity in the half plane of convergence. Plane of convergence. And in fact, the transform fs bar is the unique analytic continuation of function. Yeah, unique analytic continuation of function. Yeah, those fs is the unique continuity of function unique analytic yeah, analytic continuation of function defined by the Laplace transform. So usually the transform, for example, if you take ft, yeah, ft is equal to 1. We have seen that for this, if we find the Laplace transform of this, that give you 1 over s. Right? So usually the transform, or the Laplace transform, or the transform fs itself has a singularity. Yeah, has a singularity, but this can be in the half plane of convergence. Okay, none of this has in the half plane of convergence. So in this case, I would say fs has singularity. Of course, we can see from there when s equal to 0 is singular, but in the half plane of convergence, but in the half plane of convergence, so if you consider that for s greater than 0, so it has no singularity, but in the half plane of convergence it has no singularity. Okay, so if you look further into this thing, so if you consider the if the sigma s, let's say sigma s is the abscissa, on the rightmost singularity of fs. What does it mean? Abscissa of the rightmost singularity, of fs, then sigma s is less than sigma c, where previously we say sigma c as the abscissa of convergence. But if we have sigma s less than sigma c, whereas sigma c is the rightmost of the singularity, then sigma s itself becomes the abscissa of the convergence. Okay. Now, we usually verify the function have a Laplace transform merely by noting that the integrand, so we have the Laplace transform here, Laplace transform, to verify the function has a Laplace transform. Laplace transform. Yeah, of course we need a absolute of the function is absolute, integrable, and so on. By noting that, yeah, by noting that e minus sigma t ft goes to 0 as t goes to infinity. So this part is quite important for the large value of sigma. Yeah, large value of sigma. Those things. Even it is not a necessary condition, but it's sufficient. So the condition satisfied if, yeah, so the condition is satisfied if and only if we have absolute of ft less than some number m ect. Yeah, some number m for t greater than or equal to L. Yeah, for some value of for some value of m, c, and L. Could be very large. So we abbreviate this. So we abbreviate this. How can I write this? We abbreviate this. Abbreviate as f is equal to order ECCT. So which means in this case we call it as f is of exponential order. Yeah, f is of exponential order. All right. So if you have some number, let's say b, which is greater than c, if you have some number b greater than c, then f of exponential order ct implies that f is of exponential order of pt. Alright. Now, so we can write the exponential order of alpha, say, exponential order of alpha, exponential order of alpha, we can write as a EO exponential order f. This is equal to alpha. Now, for example, if we consider two functions, let's say t, ft, let's say t e to 2t, and the other one is ft equal to t e to t over t. One of these is exponential order 2t, but the other one is not. Can you figure out why? Can you figure out why? Remember that we need that as a sufficient condition. Even it is not necessary, but we need this as a sufficient condition here. Alright? So in this case, in these two examples here, one of these is of exponential order and the other one is not. Now, how to look at this? For this function, yeah, if you write in terms of put the exponent on the left side, so we have e minus 2t ft. So that equal to t. So obviously in this case, that e minus 2t ft, this goes to infinity as t goes to infinity. As t goes to infinity, because t goes to infinity, all these things is equal to t. So which means that on the left side also goes to infinity. So in this case, that this ft here is not exponential order of 2t. Whereas if you look at the other function here and write in terms of put the exponent on the left side. Yeah. Whereas for those function, ft equal to e to t over t. So we can write this as a e negative 2t ft that equal to 1 over t. So obviously in this case, as t goes to infinity, so we have 1 over t, goes to infinity. So 1 over t goes to 0, which means that e minus 2t ft goes to 0. So we have those condition here. Now we have those condition here. E sigma t, negative sigma t ft goes to 0 as t goes to infinity. Alright, so that goes to infinity. So in this case, we say ft is of exponential order e to t. Alright, so I have explained to you what is the abscissor of convergence. So basically the abscissor of convergence is the number, some number, which is sigma c, that separate between the convergence and divergence of the integral. Yeah, convergence and divergence of the integral. If you still confused with that, let me try to explain again. So the Laplace transform fs, we have 0 to infinity e minus st ft dt. Okay, so if you consider the damping function sigma, where for sigma less than sigma c, for sigma greater than sigma naught, they call it as sigma naught or sigma c greater than sigma c. All right, then those integral here fs converge. Whereas for sigma less than sigma c, so you just need to change that sigma into that s, so you can see all those. Then fs diverge. All right, then in this case we say sigma c as a abscissa of convergence. All right, and we also talk on the analytic function. The Laplace transform is an analytic function on the half plane of convergence thus far, right? Then we talk on the exponential order of the function. Okay, now if you look at it a little bit further, so we have the absolute of e minus st. All right, this is just same as e minus sigma t, right? Since that, so from the triangle inequality, what we have, the absolute of integrate 0 to infinity e minus st ft dt. This is less than or equal to integrate 0 to infinity e minus sigma t ft dt. Now, if the integral on the right, which is this part, if, let me write those, integral on the right, if 0 to infinity e minus sigma t ft dt is convergent, then the integral on the left, which is that part, those e minus st ft dt is also convergence. Yeah, is also convergence. All right. So from this inequality, if the right hand side is convergent, then the left side is also convergent. So in this case, those integral we call it as a absolutely convergent. So we say it is absolutely convergent. Yeah, because we consider the absolute of all this. Okay, so you can verify that if the exponential order of f equal to alpha, see, then the Laplace transform, is absolutely convergent. Yeah, is absolutely convergence when sigma greater than alpha. So in order to show this, we consider the abscissa of absolute convergence. Yeah, let's say sigma alpha. Let's say sigma alpha. Yeah, be the abscissa, be the abscissa of absolute convergence. Absolute convergence. Which means we say sigma alpha is the abscissa of absolute convergence. So which means those sigma alpha divide the values for which the integral absolute convergence for one part and diverge for the other parts. Yeah. So in this case, which means for sigma greater than sigma alpha, yeah, for sigma greater than sigma alpha, the integral is absolutely convergent. When I say integral, means the Laplace transform, because it's involved integral, is absolutely convergent. Whereas for sigma less than sigma alpha, those integral diverge. Yeah. Integral diverge. So we have this, what we have there. So we have, if seems the alpha is the biggest one, so this less than sigma alpha, less than equal to sigma c, and less than equal to sigma s. Alright, so with this relationship between all those sigma, the abscissa, and the convergence of those integral, So I think I have to stop here for this video, just about half an hour. Then I will continue in the next video. Okay, bye bye. Thank you.